Now on to linkage isomers. Linkage isomers are isomers where a ligand can bind to a metal cation through two different atoms. We've talked about ambidentate ligands before, such as SCN- and NO2-. SCN can typically bonds through the nitrogen on most metal cations. However, SCN bonds through the sulfur on metal cations like PD2+, Ag+, PT2+, Au+, and Hg2+. These are late 4D and 5D transition metals with low oxidation states, +1 and +2. Here is an example of a linkage isomer. This palladium complex has two thiosulfates, or thiocyanates, two thiocyanoligans bonded to palladium. Now, if you change the experimental conditions, such as the temperature, you may get a flipping of the ligand so that the nitrogen is bonding to the palladium instead of the sulfur. So keep that in mind, that sometimes you can have a ligand that bonds through two different atoms. If you can form two different compounds, then that is known as they're linkage isomers. So we've looked at all the different types of structural or constitutional isomers. We now need to focus on molecules with identical formulas that have bonds that are the same between the atoms. Those are known as stereo or configurational isomers. The question is the molecule identical to its mirror image? If so, that is a geometric isomer. So, let's consider the following. Consider the following square planar complexes. ML2L'2, where M is the metal cation or atom, L and L' are two different monodentate ligands such as chloro or amine. In the first complex, you see two NH3 groups that are 90 degrees from one another. And you see two chloro groups that are 90 degrees from one another. In organic chemistry, we would say things that are bonded to the same side of an alkene are cis to one another. And that works the same way in coordination chemistry as well. Since two NH3s are bonded to the same side of the complex and are 90 degrees from one another, this is known as cis. So this would be cis-diamine, cis-dichloropplatinum 2. The trans isomer is where you have the two NH3s that are 180 degrees apart. The two chloro groups are 180 degrees apart. Trans isomers have ligands with the same identity on opposite sides of the compound. So here's the names. Cis-diamine, dichloropplatinum 2. Since this is a square planar complex, since we've defined that the two amines are cis to one another, that forces the two chloros to be cis to one another. In the other case, we have trans-diamine dichloropplatinum. If we define the two amine groups as being trans, the two chloro groups must also be trans. Now, in square planar complexes, we only have cis or trans. In octahedral complexes, we have FAC and MER isomers. Now let's consider ML3L'3, where M is the metal cation or atom. L and L' are two different monodentate ligands. In the first case, you have cobalt, where all three chloros are 90 degrees from one another. If you have a case where all three chloro groups are 90 degrees from one another, that forces all three of the NH3 groups to be 90 degrees in relation to one another. This is the FAC isomer, and it has three identical ligands on one triangular face of the compound. The MER isomer. This is where you have Cl and Cl 90 degrees from one another, Cl and Cl 90 degrees from one another. But the third chlorine-chlorine interaction, they're 180 degrees from one another. You can see that with NH3 as well. That interaction between these two NH3s are 90 degrees. Between those two NH3s are 90 degrees, but the arrangement of these two NH3s are 180 degrees. The MER isomer has three identical ligands in a plane bisecting a molecule. So if we name these two compounds, since this is the FAC isomer, FAC triamine trichlorocobalt-3 is the first one, and MER triamine trichlorocobalt-3 is the second compound. Now we need to learn how to draw geometric isomers of coordination compounds. And that's what the next part of this lecture will be about. How can we draw all the possibilities for all the possible isomers of a compound given a formula? We will start off by looking at M, A2, B2, C2, where A, B, and C are unique ligands. In the first example, let's make all the ligands trans to one another. A is 180 degrees from the other A, B is 180 degrees from the other B, and C is 180 degrees from the other C. So we say that all the ligands are trans to one another in this example. In the second one, let's now require that A is trans to A still, but we now make B cis to B and C cis to C. This is a different arrangement of ligands than this arrangement. So these are geometric isomers of one another.